All right, today we're going to be talking about weight saving and center of mass. So let's get started. So today, just to give you guys a little bit of an overview, we're going to talk about four main things. So we have why is weight saving important, general weight saving techniques, importance of your center of mass on your robot, and some intentional center of mass placement when you're catting your robot in on-shape. So just to start us off, let's talk about some benefits of weight saving. So when you have a lighter robot, generally that means your robot is capable of moving around much more easily, and it can interact with the game objects faster than say a more heavy robot. And so, as I noted here, you can do more in the same time frame, and that allows your robot to score more points in the same time that you have during a match. Additionally, it allows your drive base to be faster. So a faster drive base generally means that your drive base burns out faster because the motors need to work more to move your robot of the same weight. But if you have a lighter robot, then that allows your robot drive base speed to be a lot faster, and that also contributes to having a more effective robot during matches. Additionally, this is sort of connected to my previous point, but if you have a lighter robot, there's a less risk of motor burnout. So when you're in matches and you're using a robot a lot, sometimes your motors and your drive base burn out, and that can be really problematic because it means your drive base moves slower, is less efficient, has less torque. So when you have a lighter robot, you have those motors in your drive base, they burn out less often because it takes more time for them to burn out due to the less weight, and therefore it's a lot easier to service your robot. Additionally, if you have a lighter robot, it forces you to build more optimally. It optimizes space on your robot, it optimizes your different materials, and it leads to a cleaner design as shown here. So this is a very optimized robot. You can see it doesn't use that many C-channels and doesn't use that much structure, but it gets it done very effectively. And that's what makes it such an optimal robot for a game, which is Overrun in this case. So I want to quickly talk about some benefits of weight saving as general techniques that you guys can use when you're building. So the first thing is, this might seem obvious, but use lighter materials. So one of the things here, so you can see these two robots. These are pretty advanced. These are from VEX the team because PBCUZ. But you can see that they use plastic very extensively in the robot and 3D printing parts, and that's legal in VEX, not necessarily in the region of VEX competition I'm doing, VEX U5, but you can see how they can optimize the robot by using a lot of these plastic parts, 3D printed parts that allows them to fit as many mechanisms on the robot as possible without having to worry necessarily about drivetrain weight. Additional thing that I find a lot of teams or rookie teams use very often is using a lot of steel in the robots, and I don't think that's necessarily their fault. VEX markets it in their beginning, I guess, packages, but I personally am not a great fan of steel because, as you can see here, the aluminum that VEX uses for their C-channels has a density around 0.0968 pounds per cubed inch, while their steel density is 0.284 pounds per cubic inch. And you can see that the steel is actually around 3 times heavier than aluminum. So theoretically, if you were to build a robot completely out of steel compared to aluminum, it would be 2-3 times heavier. And like I mentioned earlier, having a heavier robot means your robot can do less, means your motors burn out faster. It's a lot of issues. So I personally believe that unless there's a really, really good reason for using steel on your robot, for example, high strength axles, using aluminum is almost always the way to go. The second big thing is intentional bracing. So when you're bracing different mechanisms on your robot, when you're supporting different subsystems, you're designing your drive base, all that, I want you guys to take into consideration, is this bracing essential? Are we putting the C-channel in the spot because it is intentionally supporting a part of a robot and allows it to not fail, or are we putting that C-channel there just for the sake of putting the C-channel there? In that case, you don't want it on your robot because that's just extra weight. So this is the big question, how can I use the least material to support the most subsystems? And using that mentality to build your robot makes you a very effective and efficient builder when it comes to using materials. So that means using L channels and C channels, which are these, compared to 3 and 5 buys, which generally accomplish the same thing, but as you can see, they're bigger and therefore they're heavier and they take up more space, take up more weight. So you want to be very, very intentional when you use these bigger pieces. I have a reason for using a 5 buy, or I have a reason for using a 3 buy instead of going with the L channel or C channel alternative. Here's a little bit of an example. So here's just a drag base that we have as a CAD. So we can see that option one is that we brace it like this. So we have two C channels here, we have a C channel here, C channel here, and then we have a C channel across. So that's a perfectly fine way of bracing a robot. Our second example here is just a straight C channel across. So the difference in weight may not be super noticeable, but you can see here that there's actually a little bit of overlap between the C channels, and you also have additional screws that you need to connect the C channels to your drive base and all the different hardware. So going with the second example is just a better alternative because it allows you to be as efficient with weight and with your materials as possible. So these things may not seem super significant. It's just, oh, one tiny piece of C channel extra and a couple more screws. But if you keep using that mentality and say, oh, it's okay to just kind of not go for the most optimal design, all those small little gains in weight add up. And when you end up having a heavier robot than you anticipate. The third option, and this is a little bit more of an advanced technique, but is to use hardware substitution. So VEX uses generally steel, I believe steel nuts, so nylon nuts, Kep's nuts, etc., and steel screws as well. And so some teams also use, for example, nylon nuts and nylon screws, and that allows them to save weight in terms of hardware. And so, like I said, all these small differences, if you keep using like steel screws, then eventually you'll have 100, 200 steel screws on your robot. If you replace them all with nylon, that allows your robot to save like a decent amount of weight. An additional thing about this is we use aluminum nylocks compared to steel nylocks. So as we mentioned, steel is around 3 times heavier than aluminum, and if you're using nylocks a lot, it's not that hard to replace them with aluminum nylocks, but it actually does a lot to save weight. Additional thing is standoffs. This is very minor, but when you're thinking about using standoffs versus spacers, you want to be mindful because spacers are made out of aluminum and metal, while spacers are generally made out of nylon. And so when you're thinking about those, you generally want to gravitate towards spacers if you want to have a lighter robot, but that is really up to your choice. So I want to talk really quickly about your center of mass. So this is actually really important. So just to give you a little overview, just in case you don't know what the center of mass is, it's basically if you take your entire robot, where is that point where it rotates around, I guess, where your most mass, if you average all the mass on your robot, where is that concentrated? And so having a high center of mass is not really optimal because of 3 main things. One, obviously you have your robot mass high off the field, and so therefore when you're accelerating and you're turning, you have to move that inertia, and therefore you are much more prone to tipping when you're trying to move a lot of mass, and that's very high up. It's like balancing sort of a really long pencil, or just balancing, let's say, like an eraser, right? If you have that mass spread out over like a taller distance per se, then it's much more easy for that pencil to tip over. Conversely, if you have a low center of mass, it means that your robot mass, so generally you can build lower, be more compact, and have more of your heavier stuff towards the ground, and that allows it to be much more stable when you're driving around, means that your center of mass is very low, and that allows you to maneuver very well as compared to something with, I guess, a higher center of mass. Additionally, your center of mass can be shifted forward or shifted back. And so if you have a center of mass that is more forward to your front of your robot, it can cause your robot to dig into the field when you're accelerating forward because of that extra mass in the front. And therefore, it can be kind of hard when you're trying to accelerate towards a position as fast as possible. Additionally, one of the pros about having a forward center of mass is that it resists impacts very easily because all of your mass is concentrated in the front. Therefore, it is it's much harder for your robot to tip in that case. But when you're when you're trying to change velocity really quickly, you can find some issues with having it topple because one side of your robot is really light and one side of your robot is really heavy. So when you're trying to accelerate, you might find yourself flipping over when you're trying to move forward and back really quickly. Conversely, if we're thinking about the backward center of mass, it's essentially the same thing, except your robot is sort of flipped 180 degrees. So when you're accelerating forward, because your front of your robot is so light, you can sort of like pop a wheelie when you're accelerating forward because your front of the robot kind of lifts off the ground because it's so light when you're accelerating. Additionally, when you're having head-on impacts, because the front is light, you can also tip backward, and it can also topple easily when experiencing sudden change in velocity. So what does this all mean? It means that you want your center mass to be as low as possible on your robot, so have all your heavy materials at the bottom, or not even build anything high comparatively to the rest of your robot. And you want the center of mass to be centered in the middle. You don't want to be too far forward, too far back. You want it right in the middle, so you get the best of both worlds. So I want to really talk about one of the cool tools that Onshape has, which is the CAD software that we use. So we can actually use Onshape to identify our center of mass in our robot, so when we're CADing something. So this is the general process. So first, you want to highlight all the parts on your robot, and so here you go. You highlight everything in your project. You go to the bottom right, and you have this little weight thing, balance thing called display mass and section properties. And you can examine the pop-up table. So this gives you your total mass. It gives you, this is all the technical stuff. It gives you your center of mass displacement comparatively to your robot. It gives you mass moments of inertia. So this is really helpful when you're trying to do analysis. But if you just want a visual representation of your robot, you can see, you can look for the black and white sphere. It's kind of hard to see, but it's right there. So you can see across your entire robot, if you compound that, that's your center of mass, that black and white square, sorry, not square, sphere. And so you see that it's generally towards the center of the robot and it's down low. So it demonstrates that your center of mass is well placed. So when you're designing a robot, you can continually check using this tool and say, okay, do I need to place more mechanisms in the front, in the back, up top, or down low to make sure that my center of mass is perfectly where I want it? So this is a really good tool for determining how to get a really stable robot driving. So that's it. You guys have any questions? Come find me after, but thank you guys so much.